Dear students, welcome to the knowledge series. Today, let me discuss about the fuzzy extension principle. This is one of the important topic. So, before we start about the discussion on the fuzzy extension principle, let's see what exactly the slide with respect to the crisp and fuzzy it indicates. Now, the crisp as the terms you have already seen in my earlier slides on the video series. The crisp logic is basically a binary values, that is either a 0 or a 1. And on the other hand, fuzzy logic is like a value which ranges between 0 to 1. So here either 0 or 1 is the value, here 0 to 1. So that's how we try to see that if when we see, take the elements under the universe of a discourse, say a capital X is equal to say 1.3. At 1.3 we are seeing the crisp value is coming as 1, that is the highest value. And on the other hand, when we try to see the fuzzy, it has a range. It has a range on the two sides of 1 plus minus 1 if you take it, plus minus 0.1 if you take it, 1.2, and here is 1.4, and mid is 1.3. So at 1.3 you are having a maximum value, that is the membership value is 1. But at 1.2 and 1.4 you are having a membership value is equal to 0. But in between 1.2 to 1.3 and 1.3 to 1.4, you are having a range of value, so that is a different membership value. Now, when you try to see this second set of figures, here you try to see that you are having a range of value. That means 1.25 to 1.35. So this at this particular point, you are having the membership value is equal to 1 for the interval of 1.25 to 1.35. Similarly, you are also seeing that particular situations in the fuzzy that between 1.28 to 1.32 you are having a range of value which is equal to 1, and other than the 1.28 to 1.2 you are having a range of values, and at 1.2 to 1 and at 1.4 you are having a 0 values. So this is what we try to see in the case with respect to the fuzzy. Now these these are nothing but a fuzzy numbers. So fuzzy numbers are basically a fuzzy arithmetics, and a fuzzy number actually is a subset of the universe of the nominal numbers or a universe of a discourse. So the fuzzy integer is a fuzzy subset of the domain of integers. So that is what we termed as a fuzzy integer is nothing but a subset of the domain of integers. Now if you see further, the fuzzy number in the case of 1.3 is a single number, but here you are having a range of value which is equal to 1. The same thing is what you can see in these two figure. When we try to see that if you are taking a 1.25 to 1.35, here 1.28 to 1.38 you are having a range of values. So something we get an idea about this fuzzy number to give some certain relationship between the crisp and the fuzzy. And not only that one, in the case of a crisp at 0 and at 1 you get the same fuzzy relations, but other than that the intermediate point, that is 1.2 to 1.28 here, or 1.2 to 1.3, the similarly 1.3 to 1.4 or 1.32 to 1.4, you have some certain relationship that has to represent in terms of membership representation functions, or we say that for a given given element that is a crisp input, we get a corresponding membership output, and that membership output depend upon the slope. If this slope varies, accordingly the membership functions values varies. So this idea of the fuzzy was brought by Dr. Lothi Bhaskar Zade under the area of discussion on fuzzy extension principle. If you see this statement, the extension principle was developed by Zade in the year 1975 to extend the domain of a function on fuzzy set. It generalizes a common point-to-point mapping of the function f, that is just like a dot point where you are denoting in terms of a mapping to mapping between the fuzzy set. That means all the all the elements you are going for a mapping. It's not a null set. Rather, it has a set and it is mapping with the fuzzy sets. Now, to understand these particular situations, let's see over here. Now, in this figure, you can see a X is been shown, the set of crisp element, and here at the Y you are seeing the membership functions which is normally represent. However, here a function is drawn, nonlinear function is being represented in form of a graph, and a particular delta value is selected for a crisp element, and for that crisp element of a delta value, a corresponding membership functions is being shown. So that is being shown here. That means the Y is depend upon the functions for a given input I. So I is depend upon a function, and that functions variable is nothing but the given I. Now, what exactly it implies? That it provides a mapping by a general functions. That means if we say that f where y is equal to f of I, if the input I is a crisp, then the resulting output y is also crisp. So if this is a crisp, the output y is also a crisp. That means whatever the value is you are generating from here, the output y is depend upon that input. So the extension principle, it gives the idea about the mapping of the input x to the input y. Now, if you look into the further understanding of this one, if you take two sets, so let us take a set A and set B, and these two are the fuzzy set defined by the universe of a discourse x and y. So that means this is a separate universe of a discourse, and this is a separate universe of a discourse, where the input, this is represent in terms of in terms of a fuzzy plots. So based on this fuzzy, the corresponding fuzzy which is been shown on the y axis, this y axis here, it's not just talking about a membership, but relations between these two. Just like here we say that y is the resulting y is based on the input I. So similarly here the resulting b is depend upon the resulting A, or resulting A depend upon the resulting B, and that resulting A depend upon B and the B depend upon A is due to the functions. If this function varies, accordingly the shape of A varies with respect to B varies with respect to A, or A varies with respect to B. That's the point of understanding. So with respect to this, if we and here the f F is a non-fuzzy transformation functions. If we consider here the F with respect to this plot, it's a non-fuzzy transformation functions between the universe of a discourse X and Y. So we say that F such that X is mapping to Y. We put F colon where universe of a discourse X maps to Y with an arrow X, arrow Y. That is what X is mapping to Y. We say that a crisp functions where F maps X to Y, that is between the X set of elements of X and set of Y elements of Y. But here in this case F says that X maps to Y under the universe of a discourse is a fussified when it is extended to act on a fuzzy set is defined between the X and Y. So this is a fuzzy set, it is defined between the X and Y. Now if you look further with respect to this extension principle, now extension principle is also shows with respect to this figure. Now if you try to look across these functions, now these functions is a nonlinear functions where a element A is selected, A and B are the point on Y is equal to f of x is a curve. So this curve is a nonlinear curve, and for based on this nonlinear curve at a point A you are getting a point B. So this derivation of y is equal to b, derivation of y is equal to b from x is equal to a and y is equal to fx. What does it mean? That here it appears that this nonlinear function is like a type 1 fuzzy set. Now if you try to take a nonlinear functions like this, and where you are having a two different levels, that is a one lower extension, lower bounded level, and here the upper bounded level. So this lower level and the upper level, this will correspondingly gives 2 points, because at this particular point it intersects here, and at this particular point intersect at the maximum. Now here at this particular point intersects here, and at this particular point it intersects here. So so among these two points you take the minimum, and if you are taking among these two the maximum, then you will find these 2 points, and here the similar A and B is coming. So here you try to see the width of the A. This width of the A is different as compared to the width of the B. So A and B are the intervals y is equal to y is equal to fx is an interval valued functions. So this is a point function, this is an interval valued function, something like a how you see like a type 1 fuzzy set and a type 2 fuzzy set variation. So these deviations you can try to observe in this particular case. Now if you go further, if you try to see the fuzzy mapping, let's take a function, nonlinear functions. Now here if it is a conventional set of mapping, now if you try to see that a region A on the crisp set with respect on the x, where x is the set and A is the element of the given set, ranging between the one point to other, and based on the functions it generates the corresponding y, that is f of A. Now this f of A, either you can treat in terms of a membership functions if it is a fuzzy, or if it is not a fuzzy and just a plot, and you are mapping a relations between x and y, then you say that for a given A the corresponding y is showing deviations like this. So that is a given delta A, delta x of x, that is equal to A, gives a delta of y that is equal to f of A. Now if you put in terms of a fuzzy set has a, and in the fuzzy set you are drawn fuzzy plots like this one, and where you are having a set of elements and its corresponding membership values. So based on the membership value, you are getting a plot like this one, and it is something like a steps. You can try to see it's a steps. So there is no inclinations. So that means either it ranges from a 0 to 1, 0 to 1, 0 to 1, 0 to 1, like that. But every time it changes a bit. It is not changing between 0 to 1, but it changes between, if it is at this point, if it is a certain value, it switch over from 0 to say 1, and this one not 0 to 1, 0 to 0.1, and after 0.1 for a certain time again it went to 0.2. So that change is what it is being shown here, but not in the form of inclined, rather in the form of a steps. So whether it is inclined or whether it is steps, corresponding to that fuzzy membership plot, it gives the corresponding y, the similar type of plots. So this is what the extension principle. So the extension principle is basic concept of the fuzzy set theory, and that provide a general procedure for extending a crisp domain of a mathematical, you can take it at mathematical expressions to a fuzzy. So whatever you do here, if it is a crisp domain, so extending this crisp domain to a mathematical expression for a fuzzy domain, this gives a extension principle. Now, coming to the point of the extension principle further, if you try to see here, the definition of it is states in this way. As we have seen in the earlier figure discussion, is that a function f of dot is the mapping between the x and y. So that is how this x and y is being mapped. Now here, if you try to see, suppose f is a function from x to y, and a is a fuzzy set on x defined by a is equal to mu a of x1 by x1. That means at x1 you are having a membership function mu a x1 plus here next steps at x2 mu a of x2. Like that you get at every interval, then you create a. That is what. Now the extension principle state that the image of the set A under the mapping of f of dot, that means f is here, f of dot is nothing but your A. F of dot is A, can be expressed as a fuzzy set B. So from this and this you get here. So this f of dot is nothing but a fuzzy set here. You see here f of dot is A. So B equal to f of A, that is equal to mu A, that now here mu A x of 1, previously x of 1. Why it was x of 1 mu A of x1? Because at crisp element, or we have taken x and its membership function we have done. Now here this membership functions remains same, but the point y1 will change, y will change. So here mu A of at point y1 you are having a membership functions which is same as the A membership function. So B membership function is same as A membership function, only the point of y has changed. Now here you will be observing one thing is that the x here, x has stretched, whereas here y has compressed. That is the variations that has occurred because of this particular function. Assume that this function is a linear. Now this was non-linear earlier. Now if it is assumed that it is a linear, what is going to happen? You will get the exact A plot across the B, which is that means the universe of a discourse X having the a plot membership plot A will be exactly reflected the universe of a discourse Y membership plot B. That is what it means. Now let us see one example with respect to this. Now here crisp mathematics can be used for a fuzzy set, like a algebra, trigonometric, trapezoidal, etc. for a fuzzy set. Now here given fuzzy set is given minus 1 comma 0.5. What is minus 1 comma 0.5? That indicates that minus 1 is nothing but a membership elements of the universe of a discourse, an element of the universe of a discourse X of a given crisp elements X. So this is the crisp elements values. This is the membership values. That means this is what I mean to say. Here A is there, so here you are having a value that is minus 1, and for that corresponding 0.5. So similarly, you are creating 0, 0, 0.8, 1, 1, 2, 0.4. Now this is a fuzzy set that you have to note. Now here it is been mentioned that element, and here degree of membership functions. So that is has been mentioned over here. Now if you want to, here a function is given fx is equal to x square, and based on the fx is equal to x square, and based on the given fuzzy set, we have to create a new fuzzy set. So here A is what? X comma mu of x, and we have to create how our new function is, that is fx is equal to x square. That means this value is fx is equal to x square. That means all element value is going to double there or getting square. So here B set is written, it is square 1. Now membership you cannot square, and only the elements you are getting square 0, 0, because you cannot say that okay I got 0.8, so 0.8 square is equal to 1.6. So it is above the fuzzy range, that is 0 to 1, but you are showing a value 1.6, which is actually a wrong statement indicates. So based on the squaring, you get 1 to 1 and 2 become 4. Now in the fuzzy set B, you are defined the elements, but your membership values is yet to define. So now how you are going to identify these membership functions? So for this you are selecting 0. You are having how many elements? 0, 1 and 4. These 3 element has come. But in A, how many elements was there? There were 4 elements. And here you are having 3 elements. So if there are 3 elements, you will be having a 3 membership functions. So what you are going to do is that as per the definitions, membership functions of B is the maximum of the membership functions of the A. So this is the concept what we are going to use it. Now here since we on these functions we are going to apply the reverse mapping. Reverse mapping is nothing but previously we wrote y is equal to f of x. Now we are writing x is equal to f inverse of y. That is the only difference. So y is equal to f of x was written earlier. So now we are writing the reverse way. So when we are writing this one in a reverse way, so what we are going to find is that we are going to find the maximum membership functions. That means this y which we are going to identify, it is based on the highest value of the membership values. Now let us take a mu b of 0. Now when we try to take a mu b of 0, now mu b of 0 is what? Mu b of 0 is equal to 0.8. You can try to see. Mu b of 0 in the A was how much? 0.8. And why we have selected 0.8? You know, because you try to see here, mu A was mu A of x1, but then when it was a fuzzy set B, your y has changed as compared to x, but this remains same. So here the same thing is happened. Your y has changed. So here y has changed. So y previously was x was previously was 4 elements. So now y becomes 3 elements. But this mu b will be same as mu a. But so at mu b of 0 you are having a 0.8 values. So that is what you are seeing. At 0 it was 0.8. Now you are seeing mu b of 1. Mu b of 1, how many value is that? Mu b of 1, if you are trying to see that, you are having a mu a of 1 and mu a of minus 1. That means 1 and 0.5. 1 and 0.5. That is what you are going to see in the second case with respect to mu b of 1. Because here if you try to see this one, mu b of 1 as per with respect to the case with respect to this one. Now this has become double. This has where this was 0.5. So this was. Now here we have put it as mu b of 4. Mu b of 4 because at 0.4 it remains same, but since it was 2 become 4, so that's why we wrote mu b of 4. What is 4? 4 is the element. 4 is this mu b of 4 is not this 0.4 because this is a membership, whereas mu b of 4 is this element. Mu b of 1 is this one. Mu b of 0 is this 0. Mu b of 1 is this one. So when you talk mu b of 1, so whatever is this value, mu b of 1 is 0.5 is here and here 0.4. So you put mu b of 1 is 1. So you are having a 1 and 0.5. So among this one, which you are going to select, you are going to select the 1 among these two. Now next is mu b of 4. Mu b of 4 is what you are if you try to see, this is this one because this 2 become 4, so that's all. So that is equal to 0.4. So that 0.4. So you are having what is set B 0, 0.8, that is 0, 0.8, that is shown here 0.8, then 1, then it is equal to 1 comma 1, 4, then is equal to. So this is the entire things relation to the fuzzy extension principle. So I believe that extension principle concept has given an idea about why this particular extension principle one has to study, because extension principle gives an idea about how a fuzzy relationship it can able to create. Because under this fuzzy relations, we can we need to further have discussions related to the relations in the subsequent discussions. So with this, I conclude over here. Thank you.